Hi everyone, welcome to our first lecture of Math 185. So we're going to get started here in Chapter 6, so we're doing Section 6.1. So if you don't already have the guided notes out, either if you printed them or if you just have them on your screen and you're writing on your own page, whatever it may be, good idea to have these out because I'm going to be going through directly on them so that you can refer to these as you're going. You'll notice along the way here, like you can see it on the very front here, I have some graphs filled in here that are not filled in on the guided notes on your copy. I just wanted to save a little bit of time and just draw in these graphs to begin with. So if you want to pause and trace them out, it's just a couple of random curves and then some rectangular approximations just to give a rough idea. So it's not too important how you draw it. So let's go ahead and get started here. So, section 6.1, we're talking about areas between curves. So, previously, what we saw when we studied integration back in Calc 1, we studied how to find the area under a curve, and the way that we did that, right, was by taking these rectangular approximations. So we draw a bunch of rectangles, and we use those, find their area. That gives us a rough estimate to the area under the curve. And then as the number of rectangles goes off towards infinity, they become a better and better approximation until eventually, as you have infinitely many rectangles, you end up getting the exact area under the curve, and that is how we defined the integral from a to b of f of x dx. Right, that was our area under the curve. This is the integral. Okay. And we talk in Calc 1 about how to compute that, right, using antiderivatives to find it more simply rather than doing approximations all the time. So now, what we're going to be looking at in this section, areas between curves, we're still doing the same basic concept. So we're drawing a rectangular approximation beneath a curve. However, we're stopping when we get to a second curve that is beneath the first one. So here you'll notice we have f of x and g of x. And all of our rectangles go between f and g. Okay, so we're finding approximate area not just under a curve, but under one curve and above another. Okay, so between two curves, and in order to find this, all we need to do is compute the integral from a to b of the top function minus the bottom function. So top function minus bottom function. Okay. So the reason that this works is because, again, we're talking about areas under a curve. Okay. So here we have a little more kind of formal definition of what's going on. So the area of the region bounded by the curves f of x, g of x from a to b, where f and g are continuous, and f is greater than or equal to g for all x in the interval. So f is always bigger than g, or at least equal to it. Then the area of that region, A, is exactly this integral that we just wrote. So that's the integral from a to b of f of x minus g of x dx. Okay, now when both f and g are positive, so we don't have negatives thrown into the mix here, this is when we can start interpreting it as area. So if we look at just some random curve here, here's f and here's g, right, and I'm going from a to b, something like that. Okay, well, getting the area under f would give me all of this. Right, that's all the area under f, but I don't want all of that, right? I actually don't want this portion down here. I want to get rid of that, but that is the area beneath g. So what we're left with, then, is this part, right? The area between f and g. So the way that we get that is we take area beneath f, subtract the area beneath g, and then we get our area. So this is going to be the area under f minus the area under G. And how do we get area under a curve? Well, by using the integral. So this is just going to be integral from a to b of f minus integral from a to b of g. Right? And we might remember from Calc 1 that we can split up. Right? We can split up integrals across addition and subtraction. And that's basically what we just did here. We took this expression, split it up into two integrals across the subtraction. Okay, so let's go ahead and look at an example. So find the area of the region bounded above by y equals e to the x, bounded below by y equals x, and bounded on the sides by x equals 0 and x equals 1. So here we have, let me just give a rough sketch here. So 0 to 1, go to, and put 1 a little bit lower here. That's 1, say 2, something like that. So that is the line. Okay, and then the curve e to the x starts at the point 0, 1 and goes something like that. It starts growing, right, growing off exponentially like that. Heads off in that direction too. So we're bounding an area from x equals 0 to x equals 1. Okay, bounded below by y equals x, bounded above by y equals e to the x. So that is going to be this region right here. Okay, and you don't have to be able to draw it necessarily. Being able to draw these curves can be helpful. You can also use technology to do it, but just having a rough idea of what's going on with the graphs is never a bad thing. So to compute the area of this region, we just need the integral from a to b, so that's going to be from 0 to 1 of top function minus bottom function, right? So e to the x minus x dx. Alright. And now, so if you're a little rusty on your integration, now's a good time to get a refresher course. So take the antiderivative of each component. So antiderivative of e to the x is e to the x. Antiderivative of x is going to be 1/2 x squared, right? Or x squared over 2. And that's evaluated from 0 to 1. So then sub in, right, big F of a minus big F of b from fundamental theorem of calculus. So that's e to the first minus 1 squared over 2 minus e to the 0 minus 0 squared over 2. Okay, so that's going to be e minus 1/2 minus 1. So that's going to be e minus 1/2, so I'll just do e minus 1.5. And that would be the value of that area. Okay, and if you're wondering, is it okay to leave the e in there? Yes, I prefer that you leave the e in there. I would rather have exact answers rather than decimal approximations, almost exclusively. Okay, so in any general case, if you're left with a choice between leaving the exact answer, like in this case with an e, or making an approximation, I just want you to leave it exact. So leave it as e. Don't bother trying to plug and chug it in a calculator. So this is what I'm looking for. Alright, let's look at another example. So find the area of the region enclosed by these parabolas. So y equals x squared and y equals 2x minus x squared. So again, you don't have to know exactly what the picture looks like, although it is going to be helpful to know which function is on top. So we have the graph y equals x squared. Oh, zoom in a little here. X squared, something like that. The graph y equals 2x is going to look something like that. 2x minus x squared, I mean. something like that. So then this is the region in question in the middle there. Okay. Now how would you be able to tell which function is on top? Well, one good indicator is that this is a positive x squared, so we know a positive opening parabola goes like this. And this one has a negative x squared, so the leading term, right, that highest power is negative, so it's going to go like that. And if I just kind of superimpose like that, right, that tells you that the area is going to be in here. Okay, so knowing things about the graphs, how to read them in general is a good thing. So what we need to do is to set up this integral. I first need to get the bounds. Right? I need to figure out what the boundaries are here. So let me type this. Okay, so to get the bounds, we need to find where the graphs intersect. Okay, so where these graphs intersect, how we find that is set them equal to each other. Right? Find the points where they are equal. So that's going to be x squared equals 2x minus x squared. And now let's go ahead and solve this out. So add the x squared to the other side. So that's 2x squared equals 2x. I'm going to bring, instead of dividing by 2x, you might be tempted to do that, but algebraically that would be a mistake because you'd end up eliminating one of your solutions if you divide out the x. So I'm just going to subtract it all over. So it's going to be 2x squared minus 2x equals 0. And now we can factor it. And that way we don't lose any of our solutions. So factor out a 2x, and we're left with x minus 1. And that gives us, right, our first factor here, our second factor here. So we get x equals 0 and x equals 1. And those are going to be our bounds. Right? So we're going from 0 to 1. So our area is going to be the integral from 0 to 1. Again, we need to remember which function is on top. That's important. So the function on top is not necessarily the one that comes first. In fact, in this case, it's the second one is the one that's on top. So that's going to be 2x minus x squared minus the bottom function. So x squared dx. Okay, let's combine just to make it a little simpler. So integral 0 to 1, 2x minus 2x squared dx. Now we can go ahead and take an antiderivative. So that's going to be x squared minus 2/3 x cubed, evaluated from 0 to 1. That's going to be 1 minus 2/3 minus 0 minus 0. So I'm not going to get too much out of that one, but we end up getting the value 1/3. Okay, so the area of that region between the two parabolas is 1/3 exactly. Okay, so now the question is, what if it's not so clear? What if the functions aren't strictly one on top of the other at all times on the region? Okay, so to compute an area between f and g where f is bigger than g for some x values, but g is bigger than f for other x values, then we need to use the integral from a to b of the absolute value of f of x minus g of x dx. And why do we need to use the absolute value? Well, because we need to make sure that we are accounting for these areas appropriately and we're not getting opposites, right? Because if I were to look at, well, let me go ahead and just go to the next example. This will be a good one. So, right, and this is where the absolute value is f minus g when f is bigger, and it's g minus f when g is bigger. So by setting up the absolute value this way, we're guaranteeing that the top function will always come first. Okay, let me say that one more time. By setting it up using absolute value, we're guaranteeing that the top function will always come first. Okay, so in this example, you can see why this is important, and I already have a little diagram over here. So find the area of the region bounded by the curves y equals sine of x, y equals cosine of x equals 0, and x equals pi over 2. Alright, so in setting this up, the first thing that we have to do is notice that if we're starting off right here at 0, cosine is above sine. Right? Cosine has a larger value, so cosine of x is greater than or equal to sine of x on the interval all the way from 0 to pi over 4. That's the place where they intersect again. So 0 to pi over 4. And once you pass pi over 4, sine becomes larger. Right? Sine of x is greater than or equal to cosine of x on pi over 4 to pi over 2. Okay. So since they change position halfway through, we need to be mindful of that when we're setting up our formulas, right? Because if we just went forward and just did this integral like normal, you would find that we would actually get a value of 0, because it turns out the area in here would be the same as the area in here due to symmetry, but we're not going to talk too much about that. And then you would end up getting 0 for your area when clearly that's not 0, right? Because it's all above the x-axis. So let's go ahead and set this up using absolute values. So our area, so A, is the integral from 0 to pi over 2 of the absolute value of cosine of x minus sine of x dx. Okay. And you'll notice in here on my graph I labeled this one A1 and this one A2 for my two separate areas. This integral, because it represents the area between the curves, that is going to be the same thing as A1 plus A2. Okay, so the absolute value, what it's basically forcing us to do is to split this up into two integrals. One where cosine is on top, and one where sine is on top. And then we have to just add those values up, whatever we get. Okay, so let's set these up. So we have the integral, so the first one is only going from 0 to pi over 4. And this one, cosine's on top, so cosine x minus sine x dx plus from pi over 4 to pi over 2. This time sine is on top, so sine of x minus cosine of x dx. Okay, and now we take antiderivatives, so hopefully you remember your trig antiderivatives. So antiderivative of cosine is sine. Antiderivative of negative sine is positive cosine, so that's plus cosine of x from 0 to pi over 4 plus antiderivative of sine is negative cosine. Antiderivative of negative cosine is negative sine from pi over 4 to pi over 2. Okay. And then we go ahead and evaluate these. So let me just kind of hurry through this. So that's going to give us sine of pi over 4 is root 2 over 2, plus cosine of pi over 4 is also root 2 over 2, minus sine of 0 plus cosine of 0, and then plus negative cosine of pi over 4, so that's that's just 0, or excuse me, pi over 2, which is 0, and then minus sine of pi over 2, which is 1, and then minus negative cosine of pi over 4 and negative sine of pi over 4, so it's negative root 2 over 2, and another negative root 2 over 2. Alright. So, and you might notice, remember what I mentioned earlier about these areas would cancel out if you tried to do it all at the same time. Notice that this one is actually the same as this in a different order, but it is actually the same. So what we end up getting here is 2 root 2 minus 2. If you simplify that down fully. So there we have the area between the curves of sine and cosine from 0 to pi over 2, taking into account the fact that they change position. Alright. So next up in this section, we're going to look at another type of integration that allows us to work with even more functions. So some functions are more challenging to integrate as a function of x. What we can do to solve this problem is rewrite them as functions of y and integrate horizontally. Okay, so this is our first introduction into horizontal integration. So if a region is bounded by the curves f of y and g of y, and y going from c to d, where f and g are continuous, f of y is always greater than or equal to g of y on the interval, then we have this situation happening over here. So notice when I drew my rectangles, I'm going from f to g like this, and we talk about f being greater than or equal to g for all values. You have to kind of rotate your thinking a little bit on these horizontal integration problems, because we're so used to the idea of top to bottom, like that, right? So I take top function minus bottom function, but if you take this and just rotate it 90 degrees that way, what you have is this and that, and now this is quote-unquote top, and that's the quote-unquote bottom. Okay, so when we say top and bottom, what we really mean is closest to the axis and furthest from the axis. Okay, so the quote-unquote top function is the one that's further away from the axis, in this case the y-axis here. Right, so that's f is the further function, and g is the closer function. Okay, so you can also think of it in terms of the area, right? You have bigger area minus smaller area. Okay, so that's another way to think about it. But formulaically, to compute this area, we just take the integral from c to d of f of y minus g of y dy. Okay, and we have no problems integrating this way. We can use y as the variable. That's not an issue. As long as we're just kind of, again, rotating our thinking a little bit. You can even just tilt your head to the right, and you can see kind of what I'm talking about with that function. So let's look at an example, and an example that will actually show us why this is so useful. So find the area enclosed by the line y equals x minus 1, and the parabola y squared equals 2x plus 6. Okay, so in this case, we're going to have the graph, so the line is going to look something like this. The parabola is going to look something like this. Okay, so this is our region in here. So we need to find the area of this region. Now, here's where we need to see why this is going to be better done as functions of y instead of functions of x. So if we left these as functions of x, what we would end up having to do is we would have to compute two separate integrals. Both involving square root functions. Now, if you're thinking, wait a second, where's the square root function coming from? Well, it's coming from right here, because this is y squared. So if you're going to solve this as y equals a function of x, you're going to have to take the square root of it. So the line would be the same, so the line would just be y equals x minus 1, but the parabola would be y equals the square root of 2x plus 6. However, notice what happens over here on the left-hand side when we kind of get to right around here. Notice that the top function and the bottom function here are both the parabola. It's the same curve. So what we would have to do in order to make that work is you would have to take this as the top half of the parabola and the bottom half of the parabola. So that bottom half would be y equals negative square root of 2x plus 6. So you would have the integral between these two over here, and then another integral between these two over here. Okay, now this is doable, right? It is possible to do it this way, but I don't think that's preferable, right? If you can make the work easier on yourself, by all means, right? We don't want to overcomplicate it for ourselves if we don't have to. So what we can do is rewrite as functions of y. Okay, so the first one, we have y equals x minus 1, so rewrite that as a function of y. That's going to be x equals y plus 1. And then the second one, the parabola, we have solve it for x. That actually makes it a little bit nicer to look at. This is, rather than the square root, I mean, x equals 1/2 y squared minus 3. Alright, so move the 6 over and then divide by the 2. So we can use those instead of using the functions of x. So what that gives us, so we'll have something like this. So now we're going horizontally, and it's just one function to another function the entire way, right? The line to the parabola. So this is, right, x equals y plus 1, and this is x equals 1/2 y squared minus 3. Now the next order of business is finding the bounds. We need to find these points of intersection so that we can then use them in our integral. So let's do that. So find intersection points. So let's set these functions equal to each other. So we have y plus 1 equals 1/2 y squared minus 3. Okay, I'm going to multiply everything by 2 to get rid of that 1/2. And then just move everything to the same side. So that's going to be y squared minus 2y. Let's see, that would be a plus 2. That would be a minus 6. Subtract that over. That's going to be minus 8 equals 0. Okay, factor. It's going to be y minus 4, y plus 2, I believe. So we get y is negative 2 and y equals 4 in ascending order. Alright, so remember our bounds in this case, we're not looking at x values, we're looking at y values. So we're going from here to here with these bounds. Okay, so when we set up the integral, we're going top function minus bottom function, right? Quote unquote, top minus bottom. So it's really the function further from the axis, right, to the right, that's where the positive values are, minus the function on the left, right, closer to the negatives. So let's set up the integral for this area. So a is the integral from -2 to 4 of the outer function minus the inner function. So y plus 1 minus 1/2 y squared minus 3 dy. So let's combine as much as we can, just simplify that integrand a little bit. We get y minus 1/2 y squared plus 4 dy. Take an antiderivative, so we take them the same way that we would if it were functions of x minus 1/6 y cubed plus 4y from -2 to 4. Okay, and then use fundamental theorem of calculus to evaluate, so I'll leave that to you. And if you try it, you'll find that you end up getting the answer of 18. Okay, so that is the area between those two curves. So that's it for section 6.1. When we come back in the next section, we're going to be looking at one of our applications of integration. But that is it for areas between curves and the beginning of horizontal integration. So I'll talk with you all in the next section.